Hi friend, welcome to Math A to Z. Our today's topic is from number theory, and this is Fermat's little theorem. Let's start with the statement of this theorem. The statement is, if P be a prime and suppose P does not divide A is any integer, then A to the power P minus 1 is congruent to 1 mod P. This is Fermat's little theorem. Now start the proof of this theorem. We first consider P minus 1, first P minus 1. First P minus 1 multiple of A, that is A, 2A, 3A to P minus 1 to A. Now if we divide A, 2A, 3A to P minus 1 to A, this P minus 1 numbers by P, then we get 1, 2, 3 to P minus 1 as remainder. That is, we say that if we divide this number, and we get this remainder, but not in this order. That is, we may get the remainder when divided A by P, we may get 3, or we may get 4, or we may get 1 in this order. Okay? Not in this order. Here we say two things behind this logic. Since P does not divide A, so we cannot get remainder 0 when divide A to P minus 1A by P. Okay? And here is not 0. And we know that when we divide by the prime P, then we get the remainder as 1, 2, 3 to P minus 1, all the remainder here. And here no two of them are congruent to P. That is, if we take RA congruent to SA mod P, we get R congruent to S mod P. We cancel A because GCD of AP equal to 1, since P is prime and P does not divide A. That is 1, 2, 3 to P minus 1 are congruent modulo P. But this is not possible. So we say that the remainders are 1, 2, 3 to p minus 1. From this logic, not congruent to 0, and from this logic. Now, if we multiply in the left hand side all of them, and if we multiply in the right hand side all of them, 1, 2, 3 to p minus 1, then obviously it is congruence modulo p, and we get a to p minus 1a congruent to 1, 2, 3 to p minus 1 mod p. Okay, that is a to the power p minus 1 into p minus 1 factorial congruent to p minus 1 factorial mod p. Since p is prime, so GCD of p and p minus 1 factorial must be equal to 1. That is, we can cancel p minus 1 factorial from both sides. That is a to the power p minus 1 congruent to 1 mod p. And this is fermat-littletheorem. Okay. Now, this theorem, that is fermat-littletheorem, can be stated in more general way by dropping this term. That is, if p does not divide a, it is not given, then it is also true, and the statement of this type as if p is prime, then a to the power p congruence to a mod p for any integer a. Right? Here we get the relation of a and p as either p divide a or p does not divide a. If p divide a, then a to the power p minus a is also divide p. That is, in this case, a to the power p minus a congruent to 0 mod p. That is, a to the power p congruence a mod p. That is, in this case, it is proved. If p does not divide a, then by using fermat-littletheorem, we get a to the power p minus 1 congruence to 1 mod p. Now, if we multiply both sides by a, we get a to the power p congruence to a mod p. That is, this result is proved in this case. So, in this case, if a is any integer, then we always have a to the power p congruence to a mod p, for p must be prime. P must be prime. Okay. Now we state here another important theorem, which state that if p Q are distinct prime. And A to the power P congruence to A mod Q, and A to the power P congruence to A mod P, then A to the power PQ congruence to A mod PQ, right? PQ distinct prime, A to the power P congruence to A mod Q here, not P, and A to the power Q congruence to A mod P, not Q. Then this. Now we try to prove this statement or this theorem. From this result, we know that for any prime P and for any integer A to the power P congruence to A mod P. Now if we consider any integer as A to the power Q and prime P, then we can write A to the power Q to the power P congruence to A to the power Q mod P. Imply A to the power PQ congruence to A to the power Q mod P. And here from the given statement, A to the power Q congruence to A mod P. That is A to the power PQ congruence to A mod P. Similarly, if we take any integer as A to the power P and prime Q, then we get the result as A to the power PQ congruence to A mod Q also. And combining this result and this result, we can write A to the power PQ congruence to A mod PQ. Because we know from the theory of congruence that if A congruence to B mod M1 and A congruence to B mod M2, then A congruence to B mod M1 M2 if and only if GCD of M1 M2 equal to 1, right? So we get the result. And this theorem is very useful to prove that the converse of the Fermat-Little theorem is not true. That is converse of Fermat-Little theorem is not true. If we take 341, we say first what I can do to this converse of the Fermat-Little theorem is not true. We have to prove here A to the power P minus 1, A to the power N minus 1 congruent to 1 mod but n is composite. We have to prove this by proper example. Then we say that the Fermat-Little theorem converse is not true. We take 341 and this is equal to 11 into 31. That is a composite number. Now 2 to the power 10 equal to 1024 and this is equal to 31 into 33 plus 1. And clearly if we divide this number by 31 then the remainder is 1. That is 2 to the power 10 congruence to 1 mod 31. That is 2 to the power 11 congruence to 2 mod 31. Also 2 to the power 10 to the power 3 congruence to 1 whole cube mod 31 from this result. That is 2 to the power 30 congruence to 2 mod 31. This is congruence to 1. And 2 to the power 31 congruence to 2 mod 31. Right? Now if we divide this number by 11 then we get the result as 2 to the power 10 congruence to 1 mod 11. That is 2 to the power 10 to the power 3 congruence to 1 cube mod 1. That is 2 to the power 30 into 2 congruence to 1 into 2 mod 11. That is 2 to the power 31 congruence to 2 mod 11. Okay, and this result is not required. This result is not required. Okay. Here we get 2 to the power 31 congruence to 2 mod 11 and 2 to the power 31. Sorry, this result is required 2 to the power 31 congruence to 2 mod 31 and 2 to the power 31 congruence to 2 mod 31. Right? So by this theorem we get 2 to the power 31 2 to the power 31 into 11, that is p into q congruence to 2 mod 11 into 31. Right? That is 2 to the power 341 congruence to 2 mod 341. That is 2 to the power 340 congruence to 1 mod 341. That is 2 to the power 341 minus 1 congruence to 1 mod 341. So here n is equal to 341. That is, and a is equal to 2. That is 2 to the power 341 minus 1 conveys to 1. That is a to the power n minus 1 conveys to 1 mod n. Here also mod 341, but n is composite. We see this first. So we say that the converse of the Fermat's little theorem is not true, or may not true also. Now here we consider an interesting example of number theory. In number theory, it is given that n divides 2 to the power n minus 2. If and only n is prime. If and only n is prime. So here if and only means the converse of the little theorem is also true, but it is true only for n less equal to 340. Okay, so the converse of the Fermat's little theorem is true if the number is taken less equal to 340. But if we take n greater equal to 340, here we see if we take n equal to 341, then this is whole, but 341 is not prime. Now when a composite number, composite integer or composite number, when n be composite with n divide 2 to the power n minus 2, okay, like as n equal to 341, and this type of number in number theory called pseudo prime number. Pseudo prime. Pseudo prime number. And the smallest 4 pseudo prime number are, this is the smallest pseudo prime, and the another 3 are 561, 645 and 1105. Okay, this is 4 smallest pseudo prime number. Okay, now we consider an example from this book to explain and try to understand how we apply the Fermat's little theorem in problem. We have to verify that 17 divide 11 to the power 104 plus 1. Okay? Here 17 is prime. Also 17 does not divide 11. So Fermat's little theorem gives the result 11 to the power 17 minus 1 congruent to 1 mod 17. Okay, that is 11 to the power 16 congruent to 1 mod 17. Now we know that 11 to the power 2 equal to 121. This is congruence to 2 mod 17. That is 11 to the power 8 congruence to 2 to the power 8, that is 16 mod 17. That is 11 to the power 8 congruence to minus 1 mod 17. Now 11 to the power 8 congruence to minus 1 mod 17. And from this result we get 11 to the power 96 congruence to 1 mod 17. Now combining this result and this result, we get 11 to the power 96 into 11 to the power 8 congruence to 1 into minus 1, both are mod 17 because A congruence to B mod n and C congruence to D also mod n, then AC congruence to BD mod n from the properties of congruence. And this is 11 to the power 104 congruence to minus 1 mod 17, that is 11 to the power 104 plus 1 congruence to 0 mod 17, that is 17 divides 11 to the power 104 plus 1. Okay. Now we consider another interesting and very important theorem related to Fermat-Little theorem. If the prime P not equal to 2, okay, and GCD of AP equal to 1, A and P, here also GCD 1, then either A to the power P minus 1 by 2 congruent to 1 mod P, or A to the power P plus 1 by 2 congruent to 1 mod P. We know from Fermat-Little theorem as A to the power P minus 1 congruent to 1 mod P. Okay, and since P not equal to 2, that is P is odd, that is P minus 1 is even. So we can write this result as A to the power P minus 1 by 2 whole to the power 2 congruence to 1 mod P, because P minus 1 by 2 is an integer. Since P minus 1 is even, now we get A to the power P minus 1 by 2 minus 1 into A to the power P minus 1 by 2 plus 1 congruence to 0 mod P. That is either P divide A to the power P minus 1 by 2 minus 1, or P divide A to the power P minus 1 by 2 plus 1. Okay, if both the relation this and this hold together, then we can write P divide this also true and this also true. Then we can write P divide A to the power P minus 1 by 2 plus 1 minus a to the power p minus 1 by 2 plus 1. This minus this. So cancelling them, we get this is equal to 2. That is p divided 2. That is either p equal to 1 and p equal to 2. If p equal to 1, then not 1. So this is wrong. P be 1. And if p equal to 2, then this is not correct because p not equal to 2, it is given. So either this or this. Both the relation together does not hold. Now we consider an example which is appropriate for the last theorem. Here it is given. This is also from this book, and this is given. 7 does not divide it. Then either aq plus 1 or aq minus 1 divisible by 7. Either this or this is divisible by 7. Using Fermat's theorem, we can write a to the power 7 minus 1 congruence to 1 mod 7. That is a to the power 6 minus 1 congruence to 0 mod 7. That is aq minus 1 into aq plus 1 congruence to 0 mod 7. That is either aq minus 1 congruence to 0 mod 7 and or aq plus 1 congruence to 0 mod 7. And in similar manner, both the relation does not hold together. Because if both the relation hold together, then we can write aq plus 1 minus aq plus 1. This minus is congruence to 0 plus 0 mod 7. That is 2 congruence to 0 mod 7. But this is impossible or this is wrong. So we prove that either this or this. So this is the problem. Thank you. And the link of the handwritten note of this class, that is Fermat's theorem, proof, and related all the theorem with proof, and some important problems solved from this book are given in the description. Thank you for watching.